In this video, we're going to talk about FairCom's binary buffer, which is the secret sauce of FairCom's engine. Before I do that, I want to kind of review very quickly what we talked about in the last video, which is FairCom's engine is a general purpose engine that is really the same engine that's under most databases today, most general purpose databases like Oracle, SQL Server, MySQL, Postgres. Those are relational SQL engines. The FairCom has at its heart an ISAM engine, and what it does is it has tables, it has records in the tables, it has columns in the records for data, and it has indexes that allow you to index any column. And you can have lots of columns in a table. You can have 2,500 columns in a table. You can have 500 indexes. You know, unlike these specialty databases, you would get maybe one secondary index or two secondary indexes, and it doubles your storage and costs you lots of extra money. That's not the case here. You can have as many indexes as you really could imagine you'd ever want. You can have as much columns. You have a lot of flexibility and power. So this is our general engine. But what makes FairCom unique is this binary buffer. So what in the world is a binary buffer? Well, back 40 years ago when Bill Fairman designed this API, this ISAM API on top of this, he did it in C, and C is all about binary data. So in C, you can have a data structure. I'm just going to do it kind of JSON style because that's what most people are familiar with. But in it, you'd have different fields. So you would have a record would consist of, say, the ID field, and then that would have a certain data type. For example, it would have a big integer, which is like a 64-bit integer. And then you would have a name. And then the name would have a type, and that would be a string of some kind. Like string may be limited to 100 max characters if you're doing SQL. And then you'd have a ranking. A ranking could be which athlete ranks higher than the other athletes. And then that would be, say, an integer, normal integer. In fact, a small integer would be ideal. You're not going to have massive amounts of rankings. So a small int would be a 2-byte integer. And then you could have a salary. That could be a money field, or rather income. So we could talk about not their salary, but their overall income. And that's a big money number. So we could use a money type. Now here I'm using SQL versions. You know, in C you would have this would be an 8-byte integer. And a string would be a char, an array of char. And you can specify the size of the array. And then here you have a small integer, which is a 2-byte integer. And then money is a special FairCom type that is a decimal, large decimal, a base 10 number that can hold up to 31 digits. 31 base 10 digits of precision. So which is way bigger than even an 8-byte integer can do, which are huge. So in C, you'd build a structure like this, and you'd say, that's my record. And the cool thing about C is all these are is memory offsets to a buffer. And in C, everything's a buffer. And a buffer is just an allocated amount of RAM. So in C, if you create this structure, the C compiler knows, okay, I need so many bytes for each one of these things. And so it allocates the bytes in RAM, and you have it. And then it knows the offsets of each of these things in that structure. And it knows the data type. So it knows, okay, money is a FairCom type, because we actually have a type that does this. And we call the certain functions that you can process money using FairCom's type. We give you all those functions. So in C, all you do is you take a buffer. So a buffer is a set of bytes. And in the buffers, you carve it up and say there's so many bytes for each of these things. You stick the different parts in each of the offsets in the buffer. And here's the magic of C. If I can take any piece of memory that is the right size, and if I just load it with data, C can just point a structure to it and say, this is that structure. Done. This is the athlete structure. And you don't have to copy data. You don't have to transform data. You just simply say, point this athlete structure to this, and now interpret this as athlete. So that's what a buffer does. Now, how does this work with a database? Well, with FairCom's engine, what we do is we say we will store the data that you have in your buffer directly in the record, and that's what ISAM does. So we take your C structure here, and you store it straight into the record buffer, and it writes it to disk. And then when you read it from disk, it loads it from disk, straight binary, straight into your structure, binary to binary, straight in, no transformations, nothing in the middle. That's the secret sauce of FairCom, because our product loads data as is from disk into the structure, and you have it instantly available in your C app. So that's where we started, C applications with this binary buffer. So I call these the binary buffer APIs. We have two of them. We have an ISAM, which I've talked about, and we have we have a CTDB. CT is our original name of our product, C-tree. C for the C programming language, and B-tree for B-tree combined together to be C-tree. And so CT, we abbreviate lots of things. So that stands for C-tree, and DB stands for database. So this is our database API, and it's more relational friendly because ISAM doesn't even know about fields and data types. It literally says, you get the buffer. We put the buffer, we put whatever you stick in the buffer, we stick it on disk, and we'll index it with offsets. So ISAM just knows about offsets and a few data types. But with CTDB, you actually know about fields. It is much more strongly typed, and it has more database concepts. So it's more relational database structure. That's why the DB and CTDB. But really the principle is the same. This just adds more metadata to this buffer to say that's an ID, name, and ranking, and it tells you the types, so that the database knows more about the records than just a bunch of bytes. But these are binary buffer APIs, and these APIs literally take data off a disk into your app directly in and take it right back. At the most efficient, tuned engine possible. For 40 years, we have been tuning this thing on all the major operating systems. We support operating systems that don't even exist anymore, because we have been on over 100 operating systems. Of course, we support Linux and Windows and Mac, right? We can run on any Linux variety, including Raspberry Pis and all those things. Now, if you want to compare the buffer API to what happens in, say, a SQL engine, it's really informative to see the performance difference. The first point for the buffer API is that this engine is designed to be embedded in your application. So if you write a C application, you literally load the library into your process. So your application, instead of talking to some remote database way over here, now you can do that. FairCom DB works this way. You can have FairCom DB running over here on some other machine, and you can go across a network, and you can pay the network costs of communicating across a network, and it works fine, but you have some latency issues. Or I can run FairCom DB on the same computer as the app, and I can run it over here, separate in a separate process. So now I can use shared memory or TCP/IP, but shared memory is faster. And we do that automatically, and our APIs can talk across shared memory and be very fast. But that's still not good enough for the performance nut that I am. And so I want the API to be, and I want the database to be in process, literally embedded as a DLL linked into the app. And we have precompiled DLLs for Mac, for Windows, for Linux, just ready to go. So you can just link them right into your app, and the APIs are the same. The API for being linked in, for running here in the same computer, or running remotely is actually identical. And so it's transparent to you wherever you run. And in fact, you can run in all three places at the same time if you want it to be crazy. But the real secret of our database is that we can run embedded in process. And when you are embedded in process, I want you to think about that efficiency, because when you load that, when you have a file on disk and you're reading a record off the file, it just literally takes that byte offset we talked about. The index looks it up, get the byte offset, pulls that, grabs the data, pulls it straight into the buffer that's sitting in your application. And that buffer, if it's a C program, just sticks the structure right on top of it. Instantaneously, you have your data. So it's just the fastest possible way to get data from disk into your app and from your app back to disk. And it's all in process, and that we can get performance numbers that no other database can match. And our customers, we have a lot of customers all over the world. Many of them have said, well, we want to try a different database. And they've tried every database under the sun trying to match our performance, and they can't, because you can't get more efficient than what I just described. And you now want to compare that to, say, a SQL engine. This is true for Oracle, SQL Server, Postgres, MySQL, all the major database engines in SQL, including FairCom SQL Engine, does the following. So check this out. I'm going to erase a little bit of this here. Give me some room. All right. So when you go to make a request to a SQL databases don't typically run embedded in your application. They don't typically run on the same computer. They usually like to take over the entire computer they run on. And so they usually run on a separate computer, and they're going across the network. So what you do is you send a request over. So you write a SQL statement. So let's say we're going to do a real simple select star from athlete. So we're going to give it the most basic possible SQL query ever. And it's going to go query that table here. It's going to give me all the records. So what is it? What are the steps you have to do? First, you have to send the app. First, the app has to go create the SQL statement. Well, what is the SQL statement? Well, to create the SQL statement is ASCII text. Your app has to generate an ASCII string that looks like that and send it over. You may have there's all kinds of wrappers around that hide that from your application, but your application, those wrappers have to generate that SQL, that ASCII. That is slow. You have to convert from whatever you're using to that. That's slow. Remember, there is none of that conversions in the FairCom engine for the binary buffer APIs. You already say, give me another record, and it just comes in. Right? So that's a huge difference. Number two, you have to send the SQL to the server. Well, in the FairCom product, whether you're in process or not, you're not sending SQL somewhere else unless you're using our SQL API. You're literally saying, go get me that record. Give me the next one. Give me the next one. Give me the next one. Or use this index. Look it up and then give it to me. And it just comes in as a buffer. No translation, no languages. So that's really efficient compared to this. You send the SQL to the server. Then the server has to parse the SQL. But before it parses the SQL, the server says that's expensive. So don't just parse it. Let's look up the SQL and see if it exists in our cache. Because we don't want to parse, it's expensive to parse. So it looks it up. If it's in the cache, it uses it. If it's not in the cache, then it goes and says, let's parse it. So it parses the SQL. And of course, it's parsing text, and it has to run through a whole bunch of parsing rules because SQL can get very complicated. Started out really simple, but now it's really can get very incredibly complicated. I've got SQL statements that I've written that are pages long. I had one guy use a tool that generates SQL, and it was 30 pages of SQL. It's crazy. And we tried to optimize that, and we had to throw it away. It was impossible to optimize. So parsing SQL is a big deal. Then the engine has to go and create a plan. Some people call it an explain plan or an execution plan, but it's the plan of how am I going to go do what this asks. This doesn't tell me what to do, it doesn't tell me how to do it. It tells me what to do. It says, hey, go get me all the records from athlete. Well, how should I go get you the records from athlete? What is the best way to go do that? And there's dozens of algorithms in a SQL engine that says, okay, if you're doing this, you should do it this way, so you can get the data directly from the table. Now I want to order it. If I put an order by clause on here, it would use a different plan. If I put a where clause on here, it would filter it. It'd probably use an index, right? It's going to change the plan. So it has to figure out a plan. Parsing the SQL is expensive. Creating a plan is expensive. So this lookup, by the way, also looks up the plan, so it doesn't have to do these two steps. Then it runs the plan. Now the plan would do what FairCom does automatically. It says, go give me the next record. Well, and keep looping through till you get to the end of the file. If I want all the records. So the plan here is to go do what FairCom does naturally and loop through them all and grab all the records and bring them back. So this time the plan would say get them all. So you run the plan, and then you have to return the records. Now the records inside this database are almost always in an ISAM engine. So DB2 built their whole product on top of an ISAM engine, like FairCom's ISAM engine, but they hide the ISAM API. They hide the binary buffer API. They don't let you do the raw stuff. They do all this other stuff for you so that then they can just make your life easy. And in a lot of ways, it is easier, but you lose the control to do special things because you trust the engine to do it for you. So when you return the records, what does it have to do? It has to go convert from the binary structure that they've chosen to store it on disk, convert from that binary and convert it to what? ASCII or UTF-8 nowadays, which is way better. So UTF-8. So they're going to convert it to UTF-8 string. So they're going to have a structure that they're going to return that's UTF-8, and they're going to return that to the client. So now it's gone over here, it's done all this processing, and now it's going to send back data that the application is going to have to receive. So we're not done yet because now the application has to take these records in strings, and the app has to convert the results into binary data types that the app uses. Because the app doesn't just use string for data, it's going to go have some kind of structure. So Java is going to have its type of integers, its strings, and these are all the internal structures, and it has to convert these data types into the native data types in your language. That's another conversion step. Now look at all these steps. All I have to do in C-Tree is just say, give me the next record, and it pops in, and I'm instantly there, and I'm using it in C. Now, can you do this in Java? What about FairCom DB in Java or .NET or in C# or in Go or Python? How did that work? Well, it's the same thing. In those other languages, they have what they call an interop layer, and they all were written originally in like C, so they can all talk to C APIs, and FairCom is a C engine completely. Everything's written in C with C APIs. So we can bring this binary buffer concept into Java and .NET and Python and PHP and Go and Rust and any language you want, because we can take the binary data and bring it straight in. And what we do in our client library, we give you a client library, and we take our binary buffer with the FairCom types in it, like the money type, which is a decimal type, and we convert that into a native type in the language. So now you get the performance of the binary buffer with just one extra step, converting that binary data into your native data. But we're not converting the data into ASCII and all these other steps. We're not doing all this unless you're calling our SQL engine, because all SQL engines do all this. So that's why you really have the advantage of multiple APIs. You have the advantage of SQL when you want the power and simplicity of select star from athlete. And then you have the lower binary buffer APIs when you want total control over looking up every record and deciding how you want to lock it, how you want to move to the next record, move to the previous record, how do you want to walk indexes. You have so much control. I don't have time to get into that level. It's amazing how much control. And as a developer, you know that algorithms are how you create faster performance. Right now, we're giving a bare metal engine that cannot be beat in performance, period. No other product can go faster than this with this raw bare metal. Now, on top of that, you get to build your algorithms on top of this low-level engine. That's really simple. It's just like get records, get next, previous, go forward, backwards, jump around. You can skip records. All that real simple stuff you can just do naturally and build your own data algorithm that allows you to create performance that no other database can do. Because you're not stuck with the built-in algorithms that SQL gives you, which they have algorithms to merge joins, to do row lookups, to do hash joins. And those are really cool algorithms that would be hard for you to write. So I'm not against the algorithms, they're awesome. But when you need to do something that the SQL Engine doesn't do, which as a developer for 30, well, almost 40 years myself, um, you need to write, you need the tool that lets you get down to the engine to write your own algorithm, because the SQL can't do it for you. And I've had to do that many times and hack my way through a SQL database like Oracle, where I had reports running in SQL that were taking months to run, literally months, because we had billions and billions and billions of records, these massive reports. And we got it down to run in days using PL SQL. But if I had the FairCom engine, I could have got that down into hours because of the control. And so you have the advantage of having SQL when you need it, binary buffer when you need the control and performance, create your own custom data access algorithms. This is not theory. We have lots of customers. We've been in business for 40 years and they love this, and they build these custom algorithms that no other database engine can do. It's like the bare metal engine to go build your own car on top of, and you can build the most amazing vehicle. But when you want the normal stuff like SQL, it's right here. We have a strong SQL engine. And then when you want super easy and friendly, my favorite, JSON. So what I did with JSON is I took all the benefits of this buffer ISAM technology and model. I wrapped it with JSON, made it so simple and easy. So you have JSON queries and you have JSON data coming back. So all your SQL data now comes back as JSON. All your buffer data comes back as JSON. So you can have data coming back as JSON, data coming back as SQL, data coming back as binary buffers, all on the same data, in the same database. And why would you want that? Well, for JSON, it's going to give you the ease of use. You're going to get the performance of the ISAM engine it's not quite bare metal total algorithmic control because we simplified it, but you have a lot of algorithmic control in the JSON. So it's a light JSON layer that's super easy and simple on top of on top of the buffer API that gives you the power and control over the binary data, but it's all JSON. You do have the overhead of parsing JSON by the engine, and the engine has to generate JSON. So, but we have high performance parsers and stuff, so it's not that big a deal, but still some overhead. So there's a cost for the JSON, but it's really easy. You have SQL when you need all the power of SQL, and you have binary buffer when you need to go low and powerful and fast on the same data in the same database. That's the secret sauce of FairCom DB. You don't have to sacrifice and say, well, I'm a SQL database, I can't go low level. Or you say, no, I'm a weird low level buffer database. What the heck is that? Or I'm a weird key value store, or I'm a weird, in-memory store, or I'm a weird wide column store, right? You can be whatever you want with FairCom DB, because you could be columnar, you could be key value, you could be JSON, you can be any of those things. But at the core, you have the buffer API when you need to get down to the middle and get the performance. So you can make your own key value, your own Cassandra, and you can have a SQL engine on top of the same data at the same time, and no one else can do that. That's the power of FairCom DB.